Hi everyone, our video today is going to cover discontinuities on graphs and how we use limits to solve them or to find them and graph around them. So one thing I want to say is that my Callahan word, a simpler word for discontinuity, I like to call it a hiccup in the graph. A little hiccup. So today we're going to be finding the hiccups on the graphs of rational functions, and I'm going to go from there. So let's do some reading. You have this packet, so we're going to read through it. These are our notes. There are two types of discontinuities you will find on the graphs of rational functions. They are vertical asymptotes and holes. And that should sound familiar from pre-calculus. This is going to be a review. Okay, so let's move on. To find either of these types, just set the denominator equal to 0 and solve for x. Next, plug those x values back into the function. If the result is 0 over 0, then you have a hole in the graph at that value of x. And if the result is any other number other than 0 over 0, then you have a vertical asymptote at that value of x. Okay. You can identify the exact location or coordinates of the hole by evaluating the limit as x approaches the x value that resulted in 0 over 0. You can find the graph's direction near the vertical asymptotes by evaluating the left and right-hand limits as x approaches the x value that resulted in a number other than 0 over 0. Okay, this is going to make way more sense when we do some examples, but it's for your reference to look back at when you're studying. I wanted to put it all in writing here for you in typed format. All right, let's define vertical asymptote. You ready? Yesterday we defined horizontal asymptote. Now we're going to define vertical asymptote. Here's the definition. The line x equals a, that's the equation of a vertical line. The line x equals a is a vertical asymptote on the graph of y equals f of x if either, and here are the two limit statements, the limit as x approaches a from the left of f of x equals plus or minus infinity, or the limit as x approaches a from the right of f of x equals plus or minus infinity. So if either of those is true, then you have yourself a vertical asymptote at x equals a. Now, let me show you this for my visual learners. If you need to pause this to copy, please do so, but I'm going to go ahead, and for my visual learners, that definition is going to look just like this. Here's your y-axis. Pull this down a little bit. There's your y-axis. Here's your x-axis, okay? So x and f of x. Now, let's put a right here, and at a, you have a vertical asymptote. Bada bing, bada boom. Here it is. Okay. Now, as your graph approaches a from, say, the left-hand side, it is going to be forced to diverge to one of the infinities. It's either going to have to go up to positive infinity, or it's going to have to go down to negative infinity. And similarly, if you're approaching a from the right, if this is truly a vertical asymptote, then you're going to diverge to positive infinity or negative infinity. So that is why the definition reads as it does. As you come into a, if you go to either of the infinities, then you're going to have a vertical asymptote. You can hear the drummers of the band behind me here. If you hear drumming, it's Friday night football and the band is warming up. Okay, let's go to our first example. We have two examples today. Here's the first one. Example 1 says, f of x equals 3 divided by x minus 2. So this is a rational function. Now let me be honest with you guys. I am really good. If you throw a linear function down, like let's just say you want me to graph, oh, let me get a different color pen here. Say you want me to graph like y equals 2x minus 4. I can graph that in like 2 seconds. I go down 4 to my y-intercept, I go up 2 over 1. If you ask me to graph a quadratic function, I just know what this looks like. I've been doing it long enough. I'm good at it. I know intuitively what that looks like because of all my work with quadratics. I'll be honest with you. If you want me to graph this function, f of x equals 3 divided by x minus 2, it's rational. It's more complicated. And I honestly, off the top of my head, probably can't graph that as quickly as I can these guys. So these steps here are going to help me to graph this function without a graphing calculator. So let's read it. It says, determine the x values where the discontinuities or the hiccups occur. And to do that, we're going to set the denominator equal to 0 and solve for x. See, this is the thing with rational functions. Every rational function has a denominator. Whenever the denominator is 0, we got something bad going on. We've got a discontinuity because when 0 is on the bottom, we're undefined. See, these don't have a bottom. So these don't have discontinuities. The linear family just cruises. So does the quadratic family. No hiccups in the graphs. But this guy right here, when you set x minus 2 equal to 0 and solve, you know that at x equals 2, 2 minus 2 is 0, there's some bad stuff going on here. Well, I don't know if it's bad, it's just weird and different. So we have a hiccup in the graph. We have an undefinedness in our graph when x is 2. Okay, let's go on to the next bullet. Okay, so fine, we know something's going on, but what? Determine what type of discontinuity you have at this x value. In order to do that, you simply take this 2 and you evaluate the function at x equals 2. In other words, you find f of 2. So f of 2, if I plug it back in, is 3 over 2 minus 2. And that's 3 over 0. So I would have known anyway that this was 0 from our previous step. But 3 over 0 tells me that I have a vertical asymptote when x equals, don't say 3. I've had students do that. It's not 3. It's back here. When x equals 2. When x equals 2, I have a vertical asymptote. Okay? So I'm going to actually jump ahead here. Let's go down to the last bullet. It says sketch the beginnings of the graph. What I want you to do here is let's start. Draw your y-axis. Draw your x-axis. And let's put 2 on here. X equals 2. 1, 2. Boom. And let's draw a vertical asymptote there. That's our hiccup. Something undefined at x equals 2. All right. Now, we go on to our next bullet. Identify the coordinates of the hole, if there is one, by evaluating a limit. Well, we don't have a hole. We have a vertical asymptote. So I'm just going to do NA for not applicable. All right. Next bullet. Evaluate the limits from the left and the right of any vertical asymptotes to determine the graph's direction as it approaches the vertical asymptote. So this is the part where, as I come into 2 from the left, where am I going? Up or down? And from the right, am I going up or down? So I need to set up my limits. So it will look like this. The limit, as x approaches 2 from the left, of my function 3 divided by x minus 2. And I will also do the limit as x approaches 2 from the right of 3 over x minus 2. As with any limit, step 1 is to plug it in. So I'm going to take a number just to the left of 2, maybe 1.9, and I'm going to stick it in here. 3 divided by 1.9 minus 2 is going to give me 3 divided by negative 0.1. Now, I can put that into a calculator, or I can just do it in my head. 3 divided by 1/10 is the same as 3 times 10. Positive divided by negative. So this right here is negative 30. So when I'm just to the left of 2 at 1.9, so I'm like right here, I'm clear down here at negative 30. Okay, but what happens if I get closer to 2? Say I make this bottom 1.99. That's going to give me negative 0.01, and this will be negative 300. And what if I make this 1.999 and I come even closer to the asymptote from the left? This is going to be negative 0.001, and this is going to be negative 3,000. So we have to keep this idea of approaching as we see what these answers are approaching. And since they're getting very small in the negative direction, I'm going to answer this limit as negative infinity. Here go the drummers. So 2 from the left, we are heading to negative infinity. So I'm going to put that on my graph. Now I'm going to turn it and do 2 from the right, coming in from the right. So if I round to tenths here, the closest number to the right would be 2.1. So I'm going to do 3 over 2.1 minus 2. That gives me 3 divided by 0.1, which is positive 30. By the same sort of thinking, I can pretty much say that this limit, as I get closer, so if I make this 2.01 minus 2, this is 0.01, and this is positive 300, and so forth. So I'm going to say that this limit, 2 from the right, is headed upward to positive infinity. These answers here are getting larger without bound as I come into the asymptote. Okay, first example done. See how now I have an idea of what the graph looks like? We're going to put more of this together and sketch a full graph on Monday, but this is just step 1 in the process. Okay, one more example to go in this lesson. Okay, example 2. F of x equals x squared plus 3x minus 10 divided by x squared minus 7x plus 10. Okay, determine the x values where the discontinuities occur, set denominator equal to 0, and solve for x. So let's see what's going on that makes the denominator bad news. Here's my denominator. I'm setting it equal to 0. When you have a quadratic, set equal to 0. One of the strategies to solve it is to factor, if it will, and indeed this factors. This factors into x minus 5, x minus 2. Negative 5 times negative 2 is positive 10. Negative 5 plus negative 2 is negative 7. After I do this, by the 0 product property, I set x minus 5 equal to 0, or x minus 2 equals 0. By solving, I end up with x equals 5 or x equals 2. 2 hiccups in my graph, but what are they? So I'm going to move on here to the type. I'm going to evaluate f of 5 as well as f of 2, but I'm going to work smarter, not harder. When I go to plug it into my function, I already know that when x is 5, the denominator is 0, and I already know that when x is 2, the denominator is 0, so I don't have to redo that. I will, however, have to put 5 and 2 into my numerator. So that will look like this. 5 squared plus 3 times 5 minus 10, and then 2 squared plus 3 times 2 minus 10, which results in 30 over 0 here and 0 over 0 here. Now we know from the front page that we read, when you get 0 over 0 as your answer, you know there is a hole when x is, boom, 2. And when you get any other number that's not 0 over 0, you know you have a vertical asymptote at that x value, which is 5. So this is what we have going on here. Okay. Identify the coordinates of the hole, if there is one, by evaluating a limit. Well, and now you hear my phone ringing on this video. Boy, I can't get a break here, can I? just turn that off for a second. Okay. We do have a hole. The hole is when x is 2. Now here's the idea, guys. So what you're going to do is, think about a graph. Let's go to x equals 2. If I have a hole at x equals 2, maybe the graph looks like this. Maybe the graph looks like this. The idea is, just because f of 2 does not exist, does not mean that the limit doesn't exist. Like, you can have a limit here, right? The y values can be approaching a certain value even though right at that x value you're not defined. So if we simply find the limit as x approaches 2 and we see what the y values are heading toward, then we know where the hole is, because that's where we're going to place it. So it's going to look like this. We're going to do the limit as x approaches 2 of the function x squared plus 3x minus 10 over x squared minus 7x plus 10. We already know that when we plug it in, we get 0 over 0. That's from up here. We already know it's undefined there. But let's get back into the limit here. From our limit studies, we know one strategy to solve a limit is to factor and reduce, and these sure do look like quadratics that will factor. So that's what I'm going to do. I'm going to factor the top into x plus 5 and x minus 2. And the bottom we already know from up above is x minus 5, x minus 2. And here it goes. Bye-bye, discontinuity. X minus 2 divided by x minus 2, which is my 0 over 0 when x is 2, crosses out. And when I plug the 2 back in again, I get 2 plus 5 divided by 2 minus 5, which is 7 over negative 3, or negative 2 and 1/3. So what does this tell me? Well, it tells me that as x comes in toward 2 from the left and the right, the y value is heading toward negative 2 and 1/3. So I'm going to label the coordinates of the hole as 2, negative 2 and 1/3. And I'm going to go down here and start sketching the beginnings of this graph. So this is what I have so far. I have x, I have f of x, and I've got a hole at x equals 2, y equals negative 2 and 1/3. There it is. Okay. Now, I also know that I've got a vertical asymptote at x equals 5. So I might as well get that on there too. 1, 2, 3, 4. At 5, I have a vertical asymptote. So I'll put that on as well. Make that a little bit darker for you. Okay? Now, my last step is to evaluate my limits as I approach that 5 so that I can see where I'm headed up or down to the infinities. So we have to set up the limit as x approaches 5 from the left and the limit as x approaches 5 from the right. Now, what we could do is for the function here, we could go clear back to the top and use the original function. That will totally work. But here's the cool thing. Because we had a hole and we removed the discontinuity here, we can use this right here, the leftovers from the step above. We can use x plus 5 divided by x minus 5 as our function now. And that is way easier to work with than the quadratic mess up top. So feel free to use the reduced function, unless you really like doing more math, which is fine, and you can use this. Okay, 5 from the left. Let's put in 4.9. 4.9 plus 5 over 4.9 minus 5 is going to give me 9.9 over negative 0.1. So that's negative 99. Now, as I add 9s to my 4.9, this is going to get smaller and smaller and smaller, making this larger and larger and larger in the negative direction. So I'm going to go ahead with negative infinity. So as I come into 5 from the left, down, down, down I go. And you can see eventually on Monday when we do the lesson, we're going to hook that into that hole, and it's probably going to come up here and approach that and go on its merry way. But for today, we just want to know that we're going down here. 5 from the right. Let's do 5.1 plus 5 over 5.1 minus 5. It's going to give me 10.1 over 0.1. That's positive 101. As this gets closer and closer to 5, this is going to get closer and closer to 0. I'm just going to make this grow to infinity. And so from the right, we're going to head up. And that's that. So this is how we start to sketch the graphs of rational functions. And look at all that limit work we had to do. That's why in calculus, when you study limits, this is a great place to study the graphs of rational functions. All right, thanks for watching.